we would like to we would like to find a potential for this conservative vector field. But before we do so, let's back up a little and introduce all the relevant concepts. So first of all, a vector field is the assignment of a vector to every point of a domain. In this case, our domain is R2, the plane, and to each point we assign a vector. And this is the mathematical abstraction for things like force fields, for example. We live in a force field, the gravitational force field. Now, we say that a vector field is conservative if it is the gradient of a scalar function phi. Let's call this function phi. So in two coordinates, in two dimensions, that would mean that its components are the derivatives of some function. If we call these components P and Q, then we see that a necessary condition for this to happen, after all, remember that phi sub x and then differentiated with respect to y is the same thing as phi sub y and then differentiated with respect to x by Clairaut's theorem, which translates to P sub y is equal to Q sub x. Okay, so this is a necessary condition. And it also happens to be sufficient in the correct kind of domain. So for example, if you have a rectangle and this condition is satisfied for a vector field, then it will always have a, it will always be conservative. It will have a potential function over that domain. But it's not true in general, meaning you can have a domain, a vector field that satisfies this condition, which is not conservative. Now, and you can see easily that for the given vector field, this condition is satisfied. So if we call this P, and we call this Q, then P sub y is equal to 1 and Q sub x is equal to 1. And of course, R square is an infinite rectangle. You can think of it this way. Certainly, there is a potential, and we will show how to find it. Okay, so this about conservative vector fields. So they're the same as gradient vector fields, but when you we call them conservative, we focus on their components rather than on the function that is generating the gradient. And sometimes that function will need a little bit of effort to find, or sometimes we don't want to reference that function directly. So let's see how we find a potential. And I'm saying a potential because if you find one and then you add any constant to it, you will have another potential. So, so what do we do here? The idea is actually pretty simple. Since y plus cosine x, or p in that case more generally, is thought to be the derivative with respect to x of the potential, we begin with a first guess for the potential by integrating p with respect to x. So we take the integral, or the indefinite integral of y plus cosine x with respect to x. And what's the idea here? The idea is pretty simple. We think of y as a constant, and we integrate this with respect to x, which gives us yx plus cosine x plus c. Well, not so fast with that c. Okay, let's see why. again, we are in this strange situation where we have two variables and we pretty much ignore one, think of it as a constant and integrate it with respect to the other. But whatever we find does not need to have just a constant in this process. You could have a full function of y and it would still not affect the relation that you found as being antiderivative of the original function p, meaning you can add any g of y, and when you take the partial derivative with respect to x, that disappears and gives you what you had, meaning the function p. But it's not just that. It's also the fact that this g of y gives us some flexibility in our choice so that we can ensure that what we found also happens to have partial derivative with respect to y equal to the other component q. Because by the process that we just did, it is ensured that what is found has as partial derivative with respect to x equal to the first component. But that's not all we want. We also want the partial derivative with respect to y to be equal to the second component, and that's what we're going to require now. And so we're going to take the partial derivative with respect to y of what we just found and set it equal to the second component, and that should help us pin down g of y. So the derivative with respect to y of this will be x plus derivative of cosine of x is 0, and then we have to take the derivative, the usual derivative, or the ordinary derivative of g of y, and that should be equal to e to the y plus x, and now the x's cancel. And this is very important for this process. If the x's do not disappear, then you will have a real problem finding the function g as a function of just y. Because one would argue, okay, so what would stop this process from being applied to every vector field, not just the conservative ones? And the answer is exactly this point. So here, if you didn't have a conservative vector field, you wouldn't have been able to find a dependence of g prime of y just upon y. Of course, here things are very simple. We can take g of y and we just take one example of it to be e to the y. And finally, the potential that we were looking for, or one of the possible potentials, if you like, is yx plus cosine x plus e to the y. Okay, sometimes people here put a plus c. We don't really need that. We were specifically asking for a potential, and that's all that we needed to do. Thanks for watching.